Good morning, students. So welcome back to laser technology sessions. So in the last class we have discussed about line broadening mechanisms. So we have derived an equation for the natural line width. So the natural line width is associated with the lifetime of the state, that is mainly the spontaneous lifetime of the excited states. Then we solve the equation, then we find the line width associated with the spontaneous emission. So this is our g of omega is a line width. So then we get the expression for the g of omega, so that gives you a Lorentzian expression. So so this is the expression we got, the final expression. So your delta omega is a full width of maximum. So if you substitute in terms of delta omega, you will get g of omega equals to 2 by pi delta omega n. So I am representing n for natural line width and 1 by 1 plus 4 omega minus omega naught square by delta omega n whole square. So your delta omega n is your full width of maximum of your line width profile. So now if you see your intensity versus frequency, so this is our Lorentz profile. So this is your full width of maximum delta omega n. So now if you compare with the Gaussian profile, so this is our Gaussian profile. So the full width of maximum is same for the Lorentzian and Gaussian line profiles, but the only difference will be the tiles. The tiles will be extended in the Lorentzian case compared to your Gaussian. Gaussian will be little sharper, your tiles, compared to Lorentzian. So this is your line width is associated with the Lorentzian function. So your full width of maximum can be measured from the your delta omega n. So that is the width associated because of your spontaneous emission. Okay, now we were going to discuss about collision broadening. So in general, we have a gaseous system. So you have random collisions occurs between different atoms. The energy levels of atoms change due to their mutual interactions. So as the energy changes, in mainly the atoms come closer, and because they has to interact each other, they come closer. That gives you the perturbation to the system. That means the other atoms energy levels will be perturbed. Okay, so as energy levels is perturbed, the frequency of emission changes during the collision time. So now you see we pick the radiating atom. So that means your atom in the excited state, it's radiating. So the radiating means it's giving a photon. So that means now consider this atom. So now the atom is radiating, so it is emitting photons, and your radiation is a sinusoidal radiation. So that means I am just assuming that you have certain coherence time. So now you come with the other atom. So these are collisions happens. Now you see during the collision process, the frequency of the emitted atom changes. If you carefully observe from this one, during the collision time, your frequency got changed and again come back to whatever the emitting radiation. So now that means that after collision, the frequency returns to its original value. So now if you consider the energy values, so now your E1 and E2 is two energy states. So the gap between the E1 and E2 gives your radiation. So when the electron or atom emitting decays to ground state, it emits the photon, right? So now when it collision happens, your energy levels got shifted because it's perturbed. Now you see during collision process, so your energy got shifted, again it will come back. So now when the energy got shifted, so now what happens to the radiation? There is a change in the energy gap. So the resultant gap will give the energy for the radiation. There are many collision events are happening. So I am considering the two collision events. So your TC represents the time between collisions. So you in your gaseous system there are many collisions happens. Now we are considering two collisions. So your Tc represents time between collisions. Your delta C represents the collision time. Okay. So that means the two events happening here. So one is collision to collision. There is a time interval is there, and when there is a collision, so the collision time will be different. Now we have two different time scales. Now you consider delta Tc, that is our collision time. So that is depending upon interatomic distances and thermal velocity. So that means your interatomic distance is larger, your collision time will be large. Similarly, it inversely proportional to your thermal velocity. So that means as your these atoms are moving, it has to acquire energy from somewhere, right? So this generally the energy is they gain from the thermal energy. So then they have a thermal velocity. So when they have a velocity, they will move. The atoms will be moved. Then they will collide with the other atoms. So now your collision time depending upon the interatomic distance as well as your thermal velocity. So now in general, in many of the systems, your interatomic distances in the terms of angstrom units. So I am just taking now example of your interatomic distance of 2 angstroms, and the velocity is moving with 500 meters per second. Okay. So now if we calculate, your collision time comes in the order of 10 power minus 13 seconds. So that it's almost less than, it's sub picosecond time scales. So this collision time is very fast. So in general, the collision times, because the interaction time between the collision, when the two atoms come closer, so they will interact with this much time. Okay. So this is the collision time, and Tc is your time between collisions, that depending upon when the next atom appears. So when there is a next atom appears in the distance, then only there will be collision happen. So that depends upon the mean free path by average thermal velocity, because all the atoms are moving. So before your mean path will define what is the collision events between the two collisions. So now if I take general example, so your mean path is order of 10 power minus 4 meters. It will vary very slow, like 10 power minus 4 to 10 power minus 6, your mean path varies. Okay, so then the same average thermal velocity, then you will get your collision time in some like 10 power minus 5 seconds to or 10 power minus 6 seconds, like in the microsecond. Now if we compare the time between your collisions and the collision time, is a huge difference. Okay, your collision time is much faster, it's almost instantaneous, and your collision between the two, like two collisions, between the two collisions, you have time gap is of order of microseconds or close to microseconds. Okay, so your mean path is nothing but the average distance traveled by a particle, where in our case it's atoms, between two successive collisions. So that is your mean free path, because of it has a certain velocity, so it will move within these time scales for this much distance. Your collision time always much less than your Tc, and also your delta Tc is random. So your collision time always random. Your collisions happen at random time scales. Okay. So why I say the random, you will see. So now this Tc is a time interval between your two collisions. So now this is your frequency of radiation. Now as you see, at the collision time, your phase is completely random. So all of a sudden the frequency is changing. It's a random frequency. Now it becomes your phase abruptly changing, and now you see at another collision again the phase will be random to the previous one. Now you see in these two cases, here the phase is almost reverse. In this case, the phase change is different. Now at even different collisions, your phase will be always giving a random phase, right? So that is why what happens now, you combine these all three waves, what happens, your coherence time will decrease. So now your coherence time will depend between your collision time, like means like between two collisions, what is the time interval, that will decide you what is your coherence time, because within this time your frequency or your phase is constant. At the collision time your phase is changing. That means this is your, in principle, your coherence time of this system. If this decreases, your coherence time decreases, now your width will increase. Okay, that we already discussed in our previous classes. So now I am taking electric field associated with it. Now your phase will change as a phi. This phi remains constant for between two collisions. That's what I mentioned here. Between these two collisions, your phi phase will be maintained. Okay, now the spectrum associated with it is your epsilon of omega equals to 1 by 2 pi between your starting time to your collision time. So for example, this is your starting, assume T naught, then this becomes T naught plus Tc. So now I am going to get the spectrum from this frequency, because that is the only frequency or only the phase is constant during the process. So now your epsilon of omega, so you substitute E of t instead of E naught e power I omega naught t plus phi. Okay, so now you will get, you solve this equation, you will get in this order of 1 by 2 pi e power I omega naught minus omega t naught plus phi e power I omega naught minus omega tc minus 1 by I omega naught minus omega. So you integrate and solve this equation, you will get this equation. So now you know that your intensity is associated with your electric fields. So it's your electric field and its complex conjugate together will give you your intensity. So in principle you can take it as a modulus of epsilon of omega square. So then you will get your g of omega. So your line shape function is your constant by omega. If you solve the equation, you will get similar omega minus omega naught whole square plus 1 by t naught whole square. Your t naught is nothing but your, depending upon your collision time, that means the collision between two events, two successive collisions, and there is a p tau c, it's a probability function to have a collisions. Okay, so that all together from 0 to infinity with the time, you will get tau naught. So this tau naught is nothing but your collision time associated with your probability function of collisions. So that gives you your tau naught. So now again you see that this function again it's a Lorentzian function. You normalize it, your line shape function, you will end up with your g of omega equals to 2 by tau naught 1 by 1 plus tau naught square omega minus omega naught whole square. So now even the collision broadening also gives you the line shape function like a Lorentzian. Okay, so now the full width of maximum is nothing but your 2 by tau naught. So that you can represent as a delta omega c. C represents for here, it's a collision. So this is our frequency distribution or your spectral distribution of a width of delta omega for collision broadening. Okay, so now we know that in principle you always have a natural line width because of the spontaneous emission. Now because of the collisions, you are actually increasing the width of your delta omega. So now what happens, your total width, so this is due to your natural broadening, and now you have a collision broadening. So now overall it will increase. So this is your due to spontaneous emission, and this is your spontaneous emission plus collision bonding. Okay, so you know that your spontaneous emission delta omega, depending upon your lifetime of the spontaneous emission, that is 1 over tau sp, and plus this is 2 over tau naught. So that is your the overall width increased due to natural line width and the collision bonding.